Welcome back. We are going to learn today neural networks. I would like to do an introduction because in the next lectures we are going to start Q-learning with neural networks and SARSA with neural networks. So let's overview what neural networks are and which type of neural network we are going to use. Basically, neural networks accept some inputs, produces some outputs, and they have neurons which are inspired by biology. Basically, one thing to know for sure is that neural networks are great function approximators. And their structure, their layers, and their neurons classify neural networks. For example, in this here figure, there is a feed-forward neural network. There is no feedback, information flows on one direction. It has one hidden layer, and it is basically this type of feed-forward neural network with one layer is a powerful neural network example. It is a very good approximator. If you add more basically hidden layers, 2, 3, 4, 5, it goes like this, then these neural networks are called deep neural networks. In our lectures, basically, we are going to use this feed-forward neural network, and it is basically neurons. We are going to use radial basis functions as their neurons. And here is one radial basis function. You have basically two parameters to consider. D to I is its center, and basically its width. You can play with D1I. If you make it small, basically its width increases like that, and if you select D1I larger, it becomes narrower. All right, so function approximation with radial basis function neural networks, feed forward. Let's say we would like to approximate this function hx, it is here, using radial basis function networks. So think about here, we have, say, 5 neurons, right? These 5 neurons, their maximum value can take up to 1. So basically, if you make this parameterization, basically these functions f1 to f5, they are here. These are our radial basis functions. Let's also include a bias term. So if you find these appropriate weights, then this can reconstruct, or approximate this function. Actually, in this very beginning example, there is no approximation error. It is a perfect. In real world, don't expect to get a perfect approximation. There will be a residual error. But in this example, I generated the perfect example. So in this case, by choosing appropriate weights to our radial basis function spread over this domain, we can approximate that function. Actually, this radial basis function networks is not limited to this example only, of course. So I would like to talk about so-called universal approximation theorem. Let H be a continuous function. So over the compact set D, basically you can think of the compact set like this here, within the context of that example. Over a compact set X belongs to D, this holds for radial basis function neural networks. And this is the basically approximation residual. And as you increase the number of neurons, this approximation error can be made arbitrarily smaller. So basically, the punchline of this universal approximation theorem is that with radial basis function neural networks, feed-forward radial basis function neural networks, you can approximate any continuous function. All right, so a couple of notes to mention. If you want to use another neural network other than this feed-forward radial basis neural networks, you can. Make sure the ones that you are going to use are also universal function approximators, so you can replace it with any type of shallow or deep neural networks. Make sure they obey to some universal function theorem, approximation theorem. Besides, in addition to neural networks, you can also approximate functions with polynomials or Fourier Taylor series. As compared to those, neural networks can better represent complex nonlinear function. As these continuous functions becomes more and more complex, I personally found neural networks are much smoother approximation without any spikes, so on and so forth. One more comment: as compared to radial basis function neural networks, polynomials can overfit to data. What I mean by that, for example, instead of fitting nicely like this is an overfitting that you see happening. And Taylor and Fourier Taylor series can also suffer from ringing artifacts. Well, basically, here is the ringing artifacts that you see here and there. I would rather have a smooth approximation like this. All right, as this being said, we completed our neural network review. Just we are going to use radial basis function as our universal function approximators, and we are going to approximate Q function with radial basis function neural networks. All right, thanks for watching. See you in next class.